So here we have 2012 October November paper 43 question number 4. It says the compound responsible for the yellow color of the spice turmeric is curcumin. Its molecular structure can be deduced from the following series of reactions. The CH3O group that is present in curcumin may be regarded as unreactive. So this CH3O group over here may be considered unreactive. So what we want to do is we want to determine the structure of curcumin, okay, which is this sort of 21 carbon compound, okay, and we're not going to determine it directly here, okay. What we're going to do is we're going to look at it backwards, okay. So curcumin is undergoing a series of reactions. So there's a series of reactions shown, right, and we're going to start at the bottom right here, okay. We're going to start at the bottom right here, okay, and we're going to work our way up to making the structure of curcumin, okay. Now the question says that curcumin and compounds A and D all react with 2,4-DNPH. Now this is a test. 2,4-DNPH is a test for carbonyl compounds, right? So what we're saying is that curcumin and compounds A and D have either aldehydes or ketones, okay? We have either aldehydes or ketones here. Okay, that's where we get a positive test with. That's where we get a positive test with 2,4-DNPH. So we have aldehyde slash ketone. We have a carbonyl compound, okay? That's true for compounds A and D, okay? It's true for compounds A and D as well as curcumin, right? Which we have right here at the top. Compounds A and B effervesce with sodium carbonate, but curcumin and compounds C and D do not. So that means that A and B are carboxylic acids. They have a carboxyl group. Carboxylic acids react with sodium carbonate. The curcumin and compound C and D do not. So there's no carboxyl group present in curcumin and compound C and D. Okay. So for A and B we have a CO2H group present. Okay. It also says the curcumin reacts with bromine aqueous and with cold dilute acidified KMnO4. Now, if it reacts with cold dilute acidified KMnO4, what group is present? We have a carbon-carbon double bond present, right? Weak oxidation to make a diol. And it reacts with bromine aqueous. Now, with bromine aqueous, we're not exactly certain what groups we have, right, in curcumin. It could be a phenol, it could be an alkene. Alkenes and phenols both react with bromine aqueous. So do phenylamine, but here there's no nitrogen. So it could be either phenol or a carbon-carbon double bond, okay? So we definitely know that we have a carbon-carbon double bond, and we may also have a phenol, okay? This could be a phenol or a carbon-carbon double bond. We know carbon-carbon double bond is definitely present, but a phenol could also be present. All right. Name the functional group common to curcumin and compounds A and D, right? Now that is compounds A and D, and curcumin all react with 2,4-DNPH. So we can say that because they all react with 2,4-DNPH, the functional group that they have in common is a carbonyl. Okay. Now this could be an aldehyde or a ketone. We'll specify when we look at the reactions. Name the functional group common to compounds A and B. Well, that's a carboxylic acid group, right? A carboxyl group, right? So we have carboxylic acids present in compounds A and B, or we can say carboxyl group. Suggest the structures of compounds B, C, and D and draw their structural formulae in the relevant boxes opposite. Now we go back and we have to determine the structures of compounds B, C, and D. Okay, so we're going to start with compound C over here. Right, now compound C forms when this dialdehyde reacts with HCN and NaCN. Now what type of a reaction is taking place here? Here we have nucleophilic addition taking place. Right? What we end up doing is we have an aldehyde, right? And that gets converted to a hydroxynitrile. Right? We have addition of HCN. Right? That happens here as well as here, right? This is a nucleophilic addition of HCN to carbonyl compounds. So what happens here is that we have a CH2. That was initially bonded to a CHO, right? But now that CHO will become a CHOH CN. So this carbon is now bonded to an OH, a CN, and an H. Same thing for this carbon, right? This carbon was a CHO, but after nucleophilic addition of HCN, it'll become a hydroxynitrile. So we have OH, CN, and H. So that's compound C. Now, what is compound B? Compound C is converted to compound B. Okay, compound C is converted to compound B, and what we notice is that there's 4 additional oxygens in compound B, and the nitrogens are no longer there. So what kind of a reaction is taking place here? We no longer have nitrogen, so the nitriles are being converted to some group. The nitriles are being converted to some group where we have a lot of oxygens. So there's hydrolysis of nitriles. There's hydrolysis of nitriles. The nitriles are being converted to carboxyl groups, right? We're making carboxylic acids here. So for each nitrile that's hydrolyzed, we'll have 2 extra oxygens and 1 additional hydrogen. So if we have 2 nitriles, we'll have 4 additional oxygens and 2 additional hydrogens. Okay, so from the molecular formula, we should be able to deduce that there is hydrolysis of nitriles. Okay. We also do know that compound B has a carboxylic acid group since it effervesces with sodium carbonate. So we can deduce this by looking at this information here or by looking at the molecular formula. These nitriles are converted to carboxyl groups. Okay, carboxylic acids are forming. So we have CH2. We have a CH2 that's bonded to a COH, H, and then we have a CO2H. Okay, same thing here. The carbon, OH remains unchanged. The H is still there, but the nitrile, the CN, becomes a CO2H. Now, what is compound D? Compound D is a little bit trickier. Okay, now if you look at compound D, let's go up a little bit, right? They've said that compound D reacts with alkaline aqueous iodine followed by H plus to form this compound here. So what group was present in compound D? Now remember, compound D reacted with 2,4-DNPH. So we know it had an aldehyde or a ketone. We know it had a carbonyl. And we also now know that it reacts with alkaline aqueous iodine. So what type of a group was present in compound D? Compound D had a methyl ketone. Now, if you remember, we talk about this iodoform reaction, right? A methyl ketone group can be converted into the salt of a carboxylic acid, by reacting it with alkaline aqueous iodine. So if we react a methyl ketone with alkaline aqueous iodine, right? If we react methyl ketone with alkaline aqueous iodine, right? We're going to get a salt of the carboxylic acid, and then when we acidify that, we use H plus, we end up getting a CO2H group. So this CO2H group was initially a methyl ketone group. Again, this CO2H group was originally a methyl ketone group. When that methyl ketone reacted with alkaline aqueous iodine, we made a salt of the carboxylic acid, right? Because the CH3 breaks off, we make triiodomethane, which is the pale yellow precipitate. The CH3 breaks off. So we make the salt of the carboxylic acid, and then when we acidify it, that salt becomes the carboxyl group, the carboxylic acid. So this guy here used to be a methyl ketone. So we can say that here in compound D, we had an OH group. Remember, the CH3O group can be considered to be unreactive, and this guy used to be a methyl ketone. So this was a COCH3. This was a COCH3, right? So you can draw it like this, or you can write down the CH3 here. Okay. So this COCH3 became a carboxylic acid when we react with alkaline aqueous iodine and then we acidify it. So we've drawn the structures of compounds B, C, and D. Now suggest suitable reagents and conditions for reaction 4. Reaction 4, okay, reaction 4 over here was the hydrolysis of nitriles, right, to make the carboxylic acid. So that would be acidic hydrolysis in this case because we're making the carboxylic acid, right, not the salt, we're making the acid. So we're going to use dilute HCl and heat under reflux, right, dilute HCl, okay, aqueous, and heat under reflux. Part C says name the type of reaction for reaction 2. Now, if you look at reaction 2, okay, reaction 2 is when compound A is being converted to compound B. Now, what type of reaction is reaction 2? Look at their molecular formula. You're going from C5H4O6 to C5H8O6. So all we're doing is we're adding hydrogens. We're just adding hydrogens. So what type of reaction is this? Reaction 2 is just reduction. It is reduction. A is being reduced to form B. Okay. So going back, we can say that the type of reaction that reaction 2 is reduction. Okay. Suggest a reagent for reaction 2. Now, if you look at the reagent for reaction 2, what group are we reducing to form B from A? Now, again, remember that compound A reacted with 2,4-DNPH. So it had a carbonyl group. Compound A reacted with 2,4-DNPH. Now, if you notice in compound B, we don't have any carbonyl carbon, whereas compound A had a carbonyl carbon. So something is happening to the carbonyl in compound A that is resulting in compound B. The carbonyl is being reduced. So what type of a carbonyl did we have here? What is that carbonyl being reduced to in compound B? Now, if we remember, carbonyl compounds are reduced to alcohols. Carbonyl compounds reduced to alcohols. Again, we know that compound A has a carbonyl because it reacts with 2,4-DNPH, whereas compound B doesn't have a carbonyl. So that means that the carbonyl is being reduced in reaction 2. Now, in this case, the alcohol that we're getting is a secondary alcohol. The carbon with the OH is bonded to 2 carbons. So we have a secondary alcohol here, which means that compound A was a ketone. Okay, we had ketone groups. These secondary alcohol groups are a result of the reduction of ketones. So that means that in compound A, I have a CH2, right? That's this guy in the middle. I have a CH2. And then this carbon was a ketone. This carbon was a ketone that became a secondary alcohol, and we still have the carboxyl groups. We still have the carboxyl groups because we still have 6 oxygens here, right? So the carboxyl groups aren't being reduced. Only the ketone is being reduced, right? We're only adding 4 hydrogens. Nothing's happened to the number of oxygens. If the carboxyl is reduced, the number of oxygens will decrease because carboxyl groups are reduced to primary alcohols. So we'll have fewer oxygens. So only the ketone is being reduced and not the carboxyl group. Okay. And the same thing here. This secondary alcohol that we have, the COH, right? This carbon, this was a ketone that was reduced to a secondary alcohol that is bonded to a carboxyl group. Okay, so this is the structure of compound A. So in reaction 2, the ketones were produced to form secondary alcohols. Okay, these groups were being reduced to form this. Okay, so then what reagent did we use for reaction 2 that ensured that we reduced the ketone but not the carboxylic acid? We can use aqueous sodium borohydride, NaBH4 aqueous. Remember, NaBH4 aqueous will reduce carbonyl compounds, but it will not reduce carboxylic acids. Okay, lithium aluminum hydride will reduce carboxylic acids as well. Okay, lithium aluminum hydride will reduce both ketones and carboxylic acids. So we can't use LiAlH4. We can only use NaBH4 over here. Okay, so for reaction 2, okay, for reaction 2 we used sodium borohydride aqueous. Okay, NaBH4 aqueous. Suggest the structure of compound A and draw a structural formula in the relevant box opposite. We've already drawn the structure for compound A, right? That's where we had the 2 ketone groups. Name the functional group in curcumin that reacts with cold dilute acidified KMNO4. We already know that those are alkenes, right? Alkenes react with cold dilute acidified KMNO4. Name 2 functional groups in curcumin that react with bromine aqueous. Now we already know that alkene will react with bromine aqueous, and they're saying there are 2 functional groups in curcumin. So the other group that we said was potentially there was phenol. Remember, curcumin only has carbons, hydrogens, and oxygens, so it can't be phenylamine, so it must be phenol. Okay, so alkenes and phenols, they'll both react with bromine aqueous. The last part says suggest a structure for curcumin and draw its structural formula in the relevant box opposite. Okay, so again we go back. Now what we have to do is we have to draw the structure for curcumin. Okay, we have to draw the structure for curcumin. The first question that I have is what group in curcumin is reacting with hot concentrated acidified KMNO4 and breaking up to form these different compounds? We're forming two different compounds. We're forming 1 mole of this and 2 moles of this compound from 1 mole of curcumin. So we've learned that carbon-carbon double bonds, can be ruptured, right, by hot concentrated acidified KMNO4. So the reaction by which this large molecule, 21 carbon molecule, is broken down into smaller pieces using hot concentrated acidified KMNO4, right, that's oxidation. It's a strong oxidation of alkenes. You know that alkenes can be broken up, right? They can be oxidized and broken down into smaller pieces if we use hot concentrated acidified KMNO4. So the double bond is reacting with the hot concentrated acidified KMNO4. Now let's look at compound A for a second. In compound A, which group or groups are a result of the reaction of curcumin with hot concentrated acidified KMNO4? It's the carboxylic acids, right? It's the carboxylic acids. We must have had a carbon atom that was bonded to one hydrogen, right? It was bonded to one hydrogen and one carbon atom. It was bonded to one hydrogen and one carbon atom. That CH group became a carboxyl group, right? When the double bond ruptured, that CH group became a carboxyl group. Remember, if we have strong oxidation of alkenes, if the carbon atom on the double bond is bonded to one hydrogen, we end up getting a carboxyl group. Again, we know that it's not the ketone in the carboxyl group. We know it's the carboxyl group and not the ketone because we know that curcumin does not have a carboxyl group. Okay, curcumin does not have a carboxylic acid. It doesn't react with sodium carbonate. So that means that the carboxyl group was a result of the strong oxidation of alkenes. That means that the carbon on the double bond was bonded to one hydrogen and then that carbon became a carboxyl group. Okay, I'm going to highlight this here. Okay, this carbon became a carboxyl group as a result of the strong oxidation of the alkene. Now this carbon is bonded to a C double bond O. Again, remember curcumin does react with 2,4-DNPH, so the ketone is still there. We have a CH2, we have another C double bond O, okay, and then this carboxyl group was also a result of the strong oxidation of the alkene. Again, because curcumin did not have a carboxyl group. So this CO2H is also the result of the strong oxidation of an alkene. It's also the result of the strong oxidation of an alkene where the carbon atom is bonded to one hydrogen atom. Okay, so this entire thing, this sort of portion of curcumin resulted in the formation of compound A. And this carbon on the double bond is bonded to one hydrogen, became the carboxyl group. Now curcumin was, when it was oxidized, it formed this 1 mole of this, and it also formed 2 moles of this compound. Now if you look at this compound here, which group was a result of the strong oxidation of alkene and curcumin? Again, it was the carboxyl group, right? It's the carboxylic acid that formed as a result of the strong oxidation of the alkene and curcumin, because this CO2H group was not present in curcumin. Again, curcumin did not react with sodium carbonate. So this carbon atom here, okay, was a CH on a double bond. That CH on the double bond was oxidized to CO2H. So this carbon atom, okay, was a CH on a double bond. So it was this guy over here, right, bonded to a hydrogen, right, and then that was bonded to this ring, right, and this ring is 1, 2, 3, 4, 5, 6, right? We have a 6 carbon ring, right, and then we have an OH group on the carbon opposite. We have an OH group on the carbon opposite. Remember, curcumin has a phenol, right, and then we have a CH3O. Okay, remember the CH3O group can be regarded as unreactive. And we're getting 2 moles of this guy. So we add one of these benzene rings on this side of the double bond, and then we have one CH on this side as well. Okay, we have one CH over here as well. Okay, again, this CH over here on the double bond becomes this carboxyl group. Okay, and then again, this carbon atom is bonded to a benzene ring. Okay, this carbon atom is bonded to a benzene ring. Okay, that's bonded to an OH and a CH3O group. So that is the structure of curcumin.